Quantum computers. A quantum computer is a kind of computer that is based on quantum binary digit, also called a qubit, rather than a binary digit called a bit. In classical computers, a bit is represented as a transistor that either has electricity flowing through it or not. This is modeled as a 0 and a 1 in binary. In quantum computers, there are a few different ways to represent the qubit. However, the difference in a quantum computer from a classical computer are the states that the bit or the qubit can be in. Where the bit can only be either a 0 or a 1, the qubit can be either a 0, a 1, or both at the same time. This strange state is due to the quantum theory of superposition. When only one bit or qubit is present, the difference in performance is negligible. But when you increase the number of bits or qubits, the difference is increased exponentially, where bits increase performance by n squared, qubits increase performance by 2 to the power of n, where n is the number of bits or qubits. This is the reason there is so much support behind this new technology. The potential computational power is a substantial improvement over its predecessor. There are many issues that physicists face when creating a quantum computer. The first issue is that of decoherence. Decoherence can be viewed as the loss of information from a system into the environment, since every system is coupled with the energetic state of its surroundings. This decoherence has the effect of losing or sharing information with the environment, which in quantum computers makes the computer lose its computations. In order to combat this issue, physicists have placed the qubits in a near absolute zero vacuum environment. This has limited the issue of decoherence. Another challenge facing physicists is designing methods for reading the qubit. The observer effect in quantum physics makes this difficult. Currently, the power of the quantum computer comes from the superposition. However, the mere act of observation of the particle makes the particle no longer superpositioned. This issue is overcome by not observing the particle until the computations are complete. Another difficult issue is that of the probabilistic nature of quantum mechanics. When designing algorithms and programs, the qubit computes all the possible answers to the problem. Then the programmer has to decide which answer is the one with the highest probability of being right. This creates a whole new way to program a quantum computer compared to a classical computer. Quantum computers currently show great potential in computing huge data sets. There are some things that traditional computers are not that good at doing. When huge calculations need to be done over and over, traditional computers take a long time because they have to do each calculation one at a time. This is where quantum computers shine. Because of the superposition state, a quantum bit is able to do multiple, if not all, the calculations at the same time. Protein folding is a great example of a computation that traditional computers are not very good at, and quantum computers would be great. The amount of computation required in order to properly fold a protein is huge. Currently, the best way to compute folding proteins was created by a programmer. He designed a computer game that rewarded human players for properly folding proteins. The players did not do the calculations, but naturally started folding proteins properly based on the rewards given in the game. A quantum computer would be great at this because it would be able to do the calculations required for protein folding very quickly. Another real-world problem that traditional computers do not do very well is long-term weather modeling. Classical computers do not compute this problem well because of the massive amount of data from all the weather inputs. A quantum computer is perfect for this computation as well. It can handle huge amounts of data with ease. This is the main reason why more than a few days out the weather report is almost always wrong. The most important aspect of quantum computing that the media and the government focus on is its ability to compute large prime factors. Currently, cryptography uses large prime numbers to validate security keys when encrypting data. If a quantum computer ever comes to fruition, this form of security would be obsolete because a quantum computer can compute huge prime numbers in seconds. This is the reason the government is investing so much into this blossoming technology. There's still much work to be done in the world of quantum computing, but with the promise of such possibility, with this technology, the research and development will continue until a full working model is produced. From that point, the technology will take off because of its great potential.